In this lab, we observed how momentum behaves before and after elastic collisions using two cards. It's important to recall that momentum is the product of mass and velocity, and we will be collecting our momentum and kinetic energy before and after the collisions with the same masses and different masses. This study showed how momentum and kinetic energy behave during a collision. It really focused on analyzing the entire interaction, not just the before and after. And they found that momentum remained conserved, but kinetic energy did fluctuate in terms of an elastic collision, which we did not really see in this lab, but it is worth mentioning. Bubbles are a great example of how momentum transfers based on mass and velocity. We can see that the balls will bounce off of each other without losing energy to, for example, heat or sound.
The materials that were used for this lab were the Pascal/Capstone application software, and this application was used to generate graphs for data analysis. Two carts were used to create a collision system between the carts. A triple beam balance was used to measure the accurate weight in grams. A track was used to allow the carts to slide and create the collision. A scientific calculator helped with quantitative calculations, and a laptop scientific journal for observations and data recording.
For the procedure, firstly, we calculated the weights of the two carts and properly entered the codes into the program to be able to calculate correctly. After that, we made sure everything was turned on and calibrated and set up properly before carefully pushing the carts together and recording the before collision and after collision values. Then we added the weights onto the two carts and repeated the experiment again, this time taking into account the added weight. Finally, after the experiment, we analyzed the information and calculated the percent error with the before and after values for both trials.
This is for data analysis of lab 8. Before we started this lab, we did have to do some calculations. We first were introduced that elastic collisions, when colliding objects, rebound without lasting deformation or generating heat, and that inelastic means that they um, do generate heat, and that when they collide, they tend to stick together or deform. But the cars that we were given weren't set up for the inelastic, so we only conducted elastic. We also had to set our capstone to record different data sets at the same on the same graph, and then we also had to use the button to have an additional or the new y-axis button, so that way we could have the blue car on one side and then the red car on the other side. And then we also inputted, as the picture shows right here, we had to input the formulas to be able to get our calculated values for our graphs that we create. So from the readings that we got using the capstone, it would help us create the additional graphs that we were creating. We created velocity, momentum, and kinetic energy. And this is just a screenshot of our formula that we had to enter into the calculator part of capstone before we started recording. And then the weight of our cars, the red car was 2.82, and then our blue card was 2.72. So after we had set capstone with the formulas, we did do a trial run, and during that trial run, we did get a graph similar to this, except for our middle graph, our momentum graph, didn't have the responding line. It only had one line rather than two. So we weren't getting the information from the red car. We went back, adjusted our formulas, and got the final formula as we had seen in the previous slide. And then from there, we tried again. And from the video, we went ahead and let go of the cars. They collided, and then they went back. And then that's how we created this graph. This is our main graph that we used to start with. So again, our cars were, the red car was 2.82 grams, and then our blue car was 2.72 grams. And then from there, this lab, we collected our momentum and kinetic energy just before the collision and after the collision. And then we did it for both cases, for the elastic collision with objects with the same mass, and then the elastic collision with objects of two different masses. So this is the one for the very first one with the same mass. We didn't add any additional weight or anything to the cars. We just let them go, and then that's the graph we got from it. So this is the first graph that we had seen in the previous slide, and then this is our first annotation with our points. But because this graph also, when we were doing the annotations and we showed our TA, Anna, she explained to us that we needed to zoom in and put them farther away. So when we were doing that, we decided to just delete it and try again so that we could start fresh with a new graph. So after we had reviewed and we showed it to our TA, Anna, she told us to try to separate the points more. So we went ahead and did that, and then we got the graph that we have now. We went ahead and annotated. So the first part of that graph is following the same. It's velocity up here, momentum, and then at the very bottom, it's the kinetic energy graphs. And it is following the similar patterns for the lines or the colors. So the red graph for velocity, red car is the red line, and then our beginning one, which our first point, our first line was 0.145. And then for our velocity for the blue car, which is our blue line, we got negative 0.231. And then for our momentum, for our red car, we have the light red line, which was 0.15. And then for our green car, our green line, which is our blue car, it was 0.06. And then for our kinetic energy, the orange line indicates our red car, and then our starting point was 0.0. And then for our blue car, the line is the light blue or the teal color, and it's a negative 0.02 is our first starting point at 7 seconds. And then, because both of them are annotated in this graph, our second point, which is after the collision, so the collision is like where the lines meet, that little point is our collision. So right after our collision, and we move the point a little more to the right, so that way we can distinguish between our before collision and our after collision, because before it was a little too close and crushed together. So once we did that, we went ahead and annotated our second point. And so for our second point, the time changed to 0.850 seconds. And so for our velocity of our red car and red line is 0.273. Our velocity for our blue car, which was our blue line, was negative 0.132. For our momentum of our red car, it was a light red line with 0.21. And then our green line, which is our blue car for momentum, is 0.06. And then our kinetic energy for that second point was our orange line, which is our red car, was 0.03. And then our teal line or the light blue line, which is our blue car, was negative 0.01. So this is our table 1, our collection of values for momentum P and our kinetic energy KE before and after collision. So this is the same weight, so we didn't add any additional weight, and it's the same red and blue cars. We used the points that we had gotten in the previous graph. We went ahead and added those points together, and then that's how we got the total. So afterwards, we continued, and now we did change the weight. We added the weights to our carts right on top, and then that way we did it again. We let them collide, and then from there we got the graphs for velocity, momentum, and kinetic energy. And then this is our continuation of our previous graph. This is our first point before collision with the added weight, and then our velocity for our blue car was the blue line, which is 0.035. Velocity for the red car, which was the red line, was negative 0.171. Our momentum for the red car, which was the red line, was 0.08. And our momentum for the blue car, which was the green line, was 0.00. Our kinetic energy for the red car was the orange line, which was at 6.0 2 to the power of negative 3, so it was really 0.00602. And then our kinetic energy was negative 0.01 for our blue car, which was the light blue or teal line. So this is our second annotation. Our first one was our first line. We passed the X, which is the collision point, and then we did another annotation or that line and our points. So our second points for our velocity of our blue line, our blue car. So as we had seen previously, this is our first table. We just added the new information with the different weights. So for our blue one, we got our momentum before was 0.0. For our red car was 0.08. So when we totaled it, it was a total of 0.08. For our kinetic energy beforehand, it was a 2.02 to the power of negative 5. So it showed like a big difference in front. And then our kinetic energy for our red was negative 0.1. So our total kinetic energy was 0.01 negative. And then after the collision, our momentum was 0.05 for our blue car, and it was 0.08 for our red car. So when we totaled those, we got 0.13. And then our kinetic energy after the collision was 0.0 for our blue car. For our red car was 0.01, and so our total was 0.01. Afterwards, we went ahead and moved to the final step of our lab, which was to create our table 2% difference of values for momentum P and kinetic energy KE before and after collision. So our same weight was momentum of 28.57%, and then our kinetic energy was a difference of negative 200%. And then for our different weight, our momentum was 62.5% difference, and then our percentage difference for kinetic energy was negative 200%.
From this experiment, we learned that momentum is largely conserved in elastic collisions. Our percent differences in momentum were 28.57% for same mass collisions and 62.5% for different mass collisions, showing that although momentum was not perfectly conserved, the results were relatively close given the limitations of experimental error. For the percent differences in kinetic energy, it was 200% in elastic collisions, so that showed a lot of energy loss, which could be due to friction, imperfect elasticity of the cards, and heat or sound generation during impact. These factors can cause deviations from the ideal theoretical values. The data we got supports the theoretical principle of momentum being conserved in all collisions, and kinetic energy is only conserved in perfectly elastic ones. Our results show real-world collisions are never perfectly elastic. However, the trends in data align with what we expect. The observed errors were likely caused by, like I mentioned, friction, imperfect alignment, and timing inaccuracies, which slightly affected our results, and the percent errors we got stem from non-ideal conditions and inaccurate measurements. So to improve this in the future, we would have to attempt to minimize friction and improve data collection and precision. Thank you.